Hello and welcome to my talk on uniqueness, continuity, and long-term behavior of Nash flows over time, where I present joint work with Neil Olver from LSE London and Leon Sehring from ETH Zurich. And the talk I want to give is motivated by traffic in two different ways. First way is that the model I want to talk about is motivated by traffic. And the second one is that the model I want to talk about is a continuous model. So traffic looks a bit like this, but of course, traffic in real world is discrete. And so the connection between the two is a very interesting question. And we provide one piece for this connection. All right, so let's introduce the model. And first of all, let's introduce flows over time. So for flows over time, we are given a graph with transit times and capacity. So the transit times are depicted here, and we assume that all capacities are just one. And then we consider some flow entering into the network with a constant rate, and then traveling over time through this network. And what can happen in this situation is that the inflow of some arc exceeds the capacity of this arc. And yeah, what does this mean? So it's a situation like here, where we enter the arc with a rate of 2, but the capacity of this arc is only 1. And what happens in this situation is that the flow which arrives at the end of the arc goes into some queue, and then only the flow from the queue can leave the arc with a rate of 1. So the particles that waited longest, they can go first, and the other one, they need to line up. So somehow we will grow a queue here, and then always the particles from this queue will proceed on their ways. All right, so this is a flow over time model, which was already introduced in the 60s by Ford and Fulkerson, and was since then studied in different ways. So on one hand in the optimization community, but also in the game theoretical community. And we want to talk about the game theoretical variant today. And to come to this variant, we need to take the perspective of a particle. So in game theory, we have always these players that act selfishly. And today a player is a tiny, small particle. Okay, and to come to this situation, we will talk about earliest arrival times. And yeah, we consider such a particle, this is the green guy, what I call a particle now, and the particle starting at time theta in S. So for this example, let's just assume it starts in S at time 0. And what we do now is we compute the earliest arrival times LV at every node V. So this means we want to know the time when this particle enters into the network at time theta, what the earliest time that it can be here, here, or here. And there's a simple formula to compute this. So what are we going to do? We will look at all incoming arcs. Then we will ask what's the earliest time that we can be at the start node of the incoming arc, plus a transit time, plus a waiting time. And this will then give us the earliest time when we can be at the end node. So for the source, it's clear. If we start at time theta, we are there at time theta. So this is somehow our start. And then we always, we can always go to the next node. So here, we can just say there's only one incoming arc. We have 0 plus 1 plus 2, which is 3. Here, we have 2 incoming arcs, this one and this one. And we get 0 plus 4, which is 4, and 3 plus 1, which is 4. We get a label of 4 here. And then lastly, here we have 2 incoming arcs. On one end, we get 4 plus 1 plus 1. So the earliest time we can be here is 4. The transit time is 1. The waiting time is 1 as well. So this will give us a label of 6. Or 3 plus 4, which is 7. So the minimum is attained in this arc. And we will give the node a label of 6. So this definition gives us, on one hand, the earliest arrival times, and thus the time when the particle can be here at the earliest, and like what situation is interesting for this particle. So how does the network look here at time 4? And on the other hand, it helps us to separate the arcs into 2 sets. And one set is the set of active arcs, and the other set is the set of inactive arcs. And active arcs are exactly the arcs that attain this minimum here. So in this example, all arcs except of this one. And inactive arcs are, this one, so arcs that do not attain the minimum. And thus arcs that do not lie on any shortest path. Okay, so with this in mind, we can now come to the actual model, can now look at Nash flows over time. So let's first look at the definition. In a Nash flow over time, all particles are on a shortest ST path. This means flow is only on active arcs. Okay, so as I said, so players or particles in game theory are selfish. They want to arrive as early as possible. So this means that at any time, every particle is on a shortest ST path. And with this other definition, which we just made, with this minimum definition, we can say, okay, this means flow is only on active arcs. And this will be quite helpful. All right. To understand this better, let's look at some small examples. So the network here, where we have only two arcs, the upper arc with a transit time of 1 and the bottom arc with a transit time of 3. And both these arcs have a capacity of 1 and the inflow into the network is 2. And we want to follow the whole situation also from some other perspective, from this perspective, where we concentrate on the labels, on these green things which we just saw, on these earliest arrival times. And yeah, what we do here is we introduce a hyperplane, a line for every arc. And these lines, they separate the plane into two regions. So this one here, this corresponds to the upper arc. And the equation for the hyperplane is LS plus 1 is equal to LT. And this one is just the transit time here. And so what does this mean? This means if we look at any point in the region above this black line, then for this point corresponding to these labels, this arc is active and it has a queue. For any point on the line, the arc is just active but doesn't have a queue. And for every point below the line, the arc is inactive. And yeah, the same is true for this hyperplane and the bottom arc. Okay, so in the beginning, we are here. We have a label of 0 here, a label of 1 here. So this means we are exactly at this point. And yeah, I mean, as we see, this arc is active, this arc isn't. Makes also sense, right? We have the possibility to, like, nothing happened. We have an empty network. We have one arc with transit time 1, one with 3. Of course, only the one with 1 is on the shortest path. And for Nash flow, this means in the beginning, we should better send all particles along the upper arc, because this is like the only shortest path. So everyone wants to go there. And what happens now is, of course, that the queue builds up, because everyone wants to go there, but the capacity is not enough for everyone. So we will get some queue. And we can even follow this quite concrete, and we can see that whenever we increase this value by 1, we will increase this value by 2. And let's look at this situation here. So here, these gray arrows, they mean what I just said. So whenever you go 1 to the right, you should go 2 up. And the green line tells us which way we went. So we started here with a label of 0 for LS and a label of 1 for LT. And then we slowly increased, like time passed, so the LS label increased, and the LT label increased then with double the speed. So this is how the situation was for us. And now we are at this point. So this is an interesting point again, because we hit this black line. And what does this mean? This means the black arc gets active. So let's look here. When a particle starts here at time 2, then going along the upper arc tells us, okay, 2 plus transit time of 1 is 3, plus a waiting time of 2 is 5. So waiting time of 2 is hidden here. So going along the upper arc results in this 5, but going along the lower arc allows us also to reach at time 5. So if we start here at time 2, if we go along this arc, we do not have to wait. We will be here at time 5 as well. So this means now both arcs are active and they both have the same length. So this means this waiting time should not increase further, because then, of course, this arc would get inactive and particles on this arc would be stupid that they wait in this long queue instead of going just along the bottom path. And yeah, so this means flow will split up 1-1 now. So the waiting time here will stay constant. And here, no queue will build up. They will just proceed. And in this situation, this means, all right, when we are here, from now on, whenever we go one to the right, we go one up, because no queues are grown. Both labels, they change with the same rate. And yeah, and our green labels, they just developed along this line. So the flow started here, hit this hyperplane, this black line, then the situation changed and we went like this, we proceeded like this. And now this is a Nash flow, it would go on like this forever. We could just increase the labels further and further. Okay, so all what I told you was already known by Koch and Scutella and Comenetti, Correa and Larrey. And what they have shown is, on one hand, that Nash flows over time can be constructed by piecewise extension in phases. And this is somehow what I just said. So we start at some point, we follow this gray vector field until we hit some black line. Then again, we follow the vector field until we hit some line. Again, we go on like this and so on. So in general, these are not lines, but hyperplanes. Okay, so they showed that Nash flows over time always exist and that they can be constructed in this way. And furthermore, they showed that for every Nash flow over time, whenever you take the derivative, or almost everywhere, the derivative fulfills a certain equation system. And the equation system is exactly these gray arrows. So this is the result of the equation system. And this means every Nash flow over time, when we consider it as a green line here, is a trajectory in this vector field. Okay, so this is this is what was known, and now I want to come to our results. And what we contribute is that we show uniqueness and continuity of this Nash flows over time, and we do so by showing also long-term behavior and then using this to prove the two. Okay, what is uniqueness? Uniqueness means that a situation like this cannot happen. A situation where when we are at this point, we could either go to the right or to the top. So this would be a highly non-unique situation, right? Because there would be different possibilities at the same point. So this is not allowed. And uniqueness is an interesting property because of what I just said. So Koch and Scutella, and Comenetti, Correa and Larrey together, they showed that this Nash flows can be constructed in with these piecewise extensions. And with uniqueness, we know also that these are like the only Nash flows. So we have a nice structure of them, we can nicely understand them. And yes, the second thing which we show is continuity. And continuity means if you look at some curve and we perturb the starting conditions a bit, then also the curves will stay close to each other. So if we start close, we will stay close. And yeah, of course, this is again an example which cannot happen because here we start kind of close, but this trajectory goes further and further away from this trajectory. So here it's already quite far away, but now we'll go on like this and then like this, and it's even further away. And when we proceed, they will diverge completely. So we show that this situation cannot happen. And this is a property which I like a lot because I think this is like a necessary property such that Nash flows over time are a meaningful model, because I mean, assume you want to somehow mimic the reality with the model. You will never, ever hit the exact reality. Like the model will always be a bit apart from the reality. And if you do not have continuity, then whatever your model predicts is like completely meaningless because reality is not exactly at your point. And if you don't know that like the points around behave similar, then yeah, whatever. So this is why I like this continuity result so much. And yeah, the last thing which we have shown is long-term behavior. And long-term behavior means that this situation cannot happen where we cycle and then go through the same phases over and over again. But yeah, it also rules out some other situations. So what does it actually say? It says a green line will at some point after finite time be in some region where it can go on forever and never hit a hyperplane again. Yeah, so this is also the result which I want to start with. And then with this one, we used this one to show the other two, and I want to talk about this connection a bit deeper. But first of all, let me mention that for long-term behavior, a big part was already known. So Comenetti, Correa, and Olver, they have already shown that if the inflow rate is less or equal to the min cut, then a Nash flow over time reaches steady state after finite time. And this means that all Qs stay constant from this time on. So in the vector field perspective, again, this means for a certain class of networks, so for all networks where the inflow is less or equal to the min cut, they had the result already. They know already that after finite time, you will be in some phase and you can go on forever. And we completed this result now to show it for all networks. So now we can show a Nash flow over time reaches steady state after finite time. But of course, we cannot hope for this result anymore, that all Qs stay constant, but instead we can show that they develop in a linear way from the certain time onwards, from the time when we reach steady state onwards. But I don't want to talk about these details now, but instead talk about the connection between long-term behavior and uniqueness. And to do so, let's try to show uniqueness in this point, in the point in the middle. So this is our point L0. And what we do to show uniqueness is, first of all, we zoom in. So we forget about this hyperplane and this hyperplane. We go so close that we just don't care anymore. So we remove unnecessary arcs. And then what we do is we call this a local network, the remaining arcs. This is a local network for this point. And so now we want to use this long-term behavior, the steady state thing. And first of all, what we know is, okay, every trajectory starting somewhere here will, after finite time, reach some phase which lasts forever. And we even know a bit more. And what we know this bit more means it will, like this steady state phase, this phase which will last forever, this is exactly the vector field in this point. And for this example, assume that is the vector field like pointing towards me, pointing out of the desktop in my direction. And let's call it lambda. Okay, so this is a situation in this point. A trajectory starting in the red point would go out of the desktop towards me immediately and then would proceed like this forever. Okay, so now consider just a random curve, a curve starting somewhere. And yeah, let's follow this for a bit. So this is this green line. We know that after some finite time theta, this line will go in the steady state direction. So it first is doing things, maybe it goes along the green line, but then spirals out a bit. And at some point it will reach the line from the red point and then also go into my direction. So after some time theta, we will know, after some time big T, we will know that for all points in time coming later, like later than this big T, this curve will go in the syn flow direction, in this direction from this red point, in the steady state direction. Okay, so what would we know next? Next we say, now consider some other curve, consider some curve starting on the line between this point and this point. And then let's say this is epsilon. Then what we know is that this curve behaves exactly as this curve. And this follows from this conic structure because we have only these black lines going through the point any longer. We got rid of all the rest. We know that they behave kind of similar. And we even know more. I mean, we know that this long green line, this reached steady state at time, after time t. But now we follow the same lines, like we go the same way, but we go along the way much faster because now we have the short ways here instead of this long ways here. And this means that instead of reaching steady state after time t, we will reach it already after time epsilon t. And this means like after a short time, we will go exactly in this direction. And yeah, but what does this mean in general? This means in general, like if we look at the trajectories around this point, then almost immediately they go into my direction, they go into the steady state direction. So they are almost immediately all the same as this one, and all the points around converge to this one. And yeah, this gives us uniqueness. And we also use this or similar to show continuity. And now let me fastly conclude. So I think I could show you an interesting connection between different problems and Nash flows over time. And uniqueness is a necessary condition such that Nash flows over time can be a meaningful model. Thank you.